Now we have learned about the electric charge and its properties. If we have a positive charge here and a negative charge placed here, then you know that there will be a force of attraction between them, or they will attract one another. And if we have a positive place here and another positive place here, then these two charges, they will repel one another. And if we have a negative charge here and a negative charge placed here, then again these two charges, they will repel one another. So this is one of the properties of electric charge. If we have positive and negative, there's a force of attraction, and if we have like charges, then there'll be a force of repulsion. Now Coulomb's law in electrostatics will give us the magnitude of the force of attraction or repulsion between the two charges. So if we have a point charge Q1 placed here and another point charge Q2 placed here, separated by distance say r, then depending upon the nature of the charge, these two charges, they will experience a force of attraction or repulsion. And Coulomb's law will give us the magnitude of this force. Then according to Coulomb's law, the force of attraction or repulsion between these two charges is directly proportional to the product of the two charges Q1 into Q2, and it is inversely proportional to the square of the distance between the two charges, which is the distance here is r. So this is Coulomb's law in electrostatics. See, it's very similar to Newton's gravitational law. Newton's gravitational law, what we have is F is directly proportional to m1 into m2, inversely proportional to r square. So here gravitational law, we have m1, m2. Coulomb's law in electrostatics, we have Q1 and Q1 into Q2. So we have a similarity here, and this is known as inverse square law, since we have this r square. So if you remove the proportionality sign, what you have is a constant k, and you have Q1, Q2 by r square. So this is the formula of Coulomb's law. F is equal to k, Q1 into Q2 divided by r square. Now if we take the product Q1 into Q2, Q1 into Q2, if this product turns out to be positive, then what does that mean? It means that the charge Q1 is negative and the charge Q2 is negative, or the charge Q1 is positive and the charge Q2 is also positive. So if we take the product negative and negative, you'll get a positive. If we take the product positive and positive, you also get a positive. So if the product Q1 into Q2 is positive, or in other words, Q1, Q2, since it is positive, it is greater than 0. So since if we have this case, then the nature of the force is repulsive. Okay, so if we have Q1, Q2, the product Q1, Q2 to be greater than 0, then the force is repulsive in nature, because we have Q1 to be negative, Q2 to be negative, so they will repel. Q1 positive or Q1 positive, Q2 positive, again here will the charge will repel. Okay, then again if we take this product Q1 into Q2, and if this turns out to be negative, then this means that either Q1 is negative and Q2 is positive, or Q1 is positive and Q2 is negative. So if you take a product negative positive, what you'll get? Negative. So positive into negative, that also will get negative. So here, if the product Q1 into Q2 is negative, or in other words, Q1 into Q2 is less than 0, then the force is attractive in nature. Okay, so we have these two cases. Q1 into Q2 is greater than 0, then the force is repulsive in nature, and if Q1 into Q2 is less than 0, then the force is attractive in nature. So now let us see about this constant K. What does this constant K gives you? Now this constant K depends upon the nature of the medium in which the charges are placed. Suppose you have two mediums, medium 1 and medium 2. And suppose the charges Q1 and Q2 is placed in this medium 1 with a distance say 1 meter. And suppose the charge on this Q1 is 1 coulomb, and the charge on this Q2 is also say 1 coulomb. So these two charges, they will experience a force of repulsions because they have both they are positive. Now if you place this same charge Q 1 coulomb, and they are separated by distance 1 meter in medium 2, then again here the force is repulsive in nature. But depending upon the nature of the medium, the force in medium 1 may be greater than the force in medium 2. Okay, and depending upon this case, if suppose in the medium 1 the value of K is much more larger than that of medium 2, then what happens is the force in medium 1 will be greater. So you can see here K depends upon the nature of the medium in which the charges are placed upon, and this K is equal to 1 by 4 pi epsilon. Now again this epsilon is known as permittivity. Okay, and this depends upon the medium in which or the nature of the medium in which the charges are placed. So if epsilon is large, K will be small, and if epsilon is small, K will be large. Right, so here if we consider free space, that is air, then this K will be equal to 1 by 4 pi epsilon naught. Now epsilon naught is the absolute permittivity of free space. Okay, so this Coulomb's law, if we take free space, if the charge they are placed in the free space or air, then your Coulomb's law will be expressed as 1 by 4 pi epsilon naught Q1 Q2 divided by R square. Now this 4 pi, where does this comes from? This you learned when we are introduced to Gauss law. Okay, we can derive this formula 1 by 4 pi epsilon naught Q1 Q2 by R square by using Gauss law. So this 4 pi comes from Gauss law. Okay, that we learned later. So this is Coulomb's law, the formula for Coulomb's law in electrostatics. F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square, provided the charges they are kept in free space or air. Now this epsilon naught, absolute permittivity of free space, has a value which is equal to 8.854 into 10 to the power minus 12. And the unit of this epsilon naught, you can find it from this formula, Coulomb's law, the formula of Coulomb's law. Now the force here is the SI unit of force is Newton. The SI unit of charge is Coulomb. So here we have Q1, Q2, so we have Coulomb square. And the SI unit of distance is meter. So here we have r square, so we have meter square. Hence we have the SI unit of this epsilon naught. We have Coulomb square per Newton per meter square. So this is the SI unit of this absolute permittivity of free space, or just permittivity. The SI unit of permittivity will be Coulomb square, then per Newton per meter square. So in free space, if we put the value of this epsilon naught, which is equal to 8.854 into 10 to the power minus 12, this you can do, you can perform this calculation by yourself. What you'll get is F to be equal to, if we put this value of epsilon naught in this formula, 1 by 4 pi epsilon naught, this 1 by 4 pi epsilon naught will be equal to 9 into 10 to the power 9. And so your Coulomb's law in electrostatics will be, if after putting the value of epsilon naught, you'll get 9 into 10 to the power 9 Q1 Q2 by R square. So this you can use this value 9 10 to the power 9 for calculation, to calculate the force of Eason calculation. For simplicity in your calculation, you just use the value of 9 10 to the power 9 directly. So that is Coulomb's law in electrostatics. Now we can define 1 Coulomb also from this Coulomb's law in electrostatics. Now we know the force of attraction or repulsion between any two charges Q1 and Q2 to separate at distance r is given as a 9 into 10 to the power 9 Q1 Q2 divided by r square, provided the two charges they are placed in the free space or in air. So now if you put Q1 and Q2 to be equal to 1 Coulomb, and if your r, the distance between the two charge Q1 Q2 is equal to 1 meter. So you put these two values, Q1 Q2 is equal to 1 Coulomb and r is equal to 1 meter in this formula. Then what you'll get, F will be equal to 9 into 10 to the power 9. 1 to 1 will give you 1. Then again here r is equal to 1. So this also will give you 1. So you'll get a force which is equal to 9 into 10 to the power 9 Newton. Alright, so here we can define this 1 Coulomb. So how do you define it? 1 Coulomb is that charge which repels an equal and similar charge with a force of 9 into 10 to the power 9 Newton when placed in the vacuum or air at a distance of 1 meter from one another, or from this charge of 1 Coulomb. Okay, so that is how you'll define this unit of charge, which is 1 Coulomb, by using Coulomb's law in electrostatics.